Okay, so let's do the question number 21. But before I actually talk about 21, I want to actually point out a few important stuff about the Gibbs free energies. So just try to look for the H2O. So take a look at H2O Gibbs free energies. I'm talking about free energy of formation, right? At the room temperature, all of these data are room temperature, right? Let me just try to make sure that it's on the screen. Yep. So this is at the room temperature, right? You notice that, can I actually write down these things? No, I can't write down. Okay, that's fine. So liquid water at the room temperature have a negative 237. The gas phase water is negative 228. You notice that the liquid water have lower Gibbs free energies. The Gibbs free energy, if the phase of the substance, right? Phase of the substance is lower, then that substance is tend to be in that form. So for at the room temperature, the H2O tend to be liquid than the gas phase. So the I hope this makes sense. It's the liquid phase is lower in energy, so the things always tend to be in a lower energy form. So the H2O is actually liquid in the room temperature. So anytime you're dealing with the two different phases like these guys, like iodine for example, you notice that iodine has the lower energies in solid. So the iodine is actually a solid at the room temperature. It's not the gas phase. Okay? So you got that. Then let's do the question number 21. So we are going to figure out, let's just say, okay, let's see that we're trying to figure out the normal boiling point. It's an interesting problem. The normal boiling point of the bromine, and assuming that delta H and delta S do not change with the temperatures. So at the boiling point, what's happening at the boiling point? The liquid and the gas can coexist, right? It's at the equal probabilities. At the boiling point, bromine could be liquid or the gas. Okay, so that means that the delta G has to be same for the liquid and gas. So let me just start writing out the stuff here on the page. So the delta, so bromine of liquid going to bromine of gas, right? At the boiling point, these two actually have delta G of formation of the Br2 of liquid is equal to delta G of formation of the Br2 of the gas, because it's at the boiling point. Okay, so what can I do here? The delta G, the problem doesn't say anything about delta G being constant, right? The delta G could actually change by the temperatures, but delta H and delta S do not change with the temperature. That's what this program says. So we're gonna deal with that. So instead of having the delta G formula here, I am going to actually change it to the delta H of formation of the, can I just put it as a liquid minus T delta S of the liquid is equal to delta H of formation of the gas minus T delta S of the gas. Good. Then we are trying to solve for this T because T has to be at the boiling point, right? At the boiling point temperature. Both of these guys, right? So delta HF of the liquid minus delta HF of the gas has to be equal to T delta S of liquid. Oops, I'm running out of the space. Can I actually make this thing a delta S of the gas? Sorry, maybe a little bit too small, but hopefully you can actually see this one. Then the T is actually given by delta H of formation of liquid minus delta H of formation of gas divided by these things, right? The delta S of liquid minus delta S of the gas. I think I did it correctly. So let's just try to get the informations for each one of these things and then put it in Excel. So let's just go to the bromine. So let me just try to get the bromine stuff. Okay, am I on this screen? No, not that. Okay. So bromine. The first column is the delta H, the last column is the delta S. These are the two things that we want, right? Because delta G may not be constant at the different temperatures, right? Delta G may change if it's not 25 degrees here, but delta H and delta S, these things tend to be constant. So we're going to use these values and these values. Okay, so the delta HF of the liquid is 0. I'm just trying to write down all the informations here. And delta H of formation is positive 30.91. Then whenever you're dealing with the thermodynamics, be very careful with signs, because the sign means positive or negative. Okay, so the liquid right here is 152.23. Note that this 152.3 is it's a joule, right? So I have to divide this by 1000. And then the delta S for the gas is 245.46. Okay, so this is pretty much all I have. So I have these values right here. So let's just calculate using the Excel. So what is the T, at the boiling point, the temperature, temp BP boiling point is equal to 0 minus actually it's capturing the screen. So it's sorry, I said something in Japanese. Then 0 divided by 0 minus 30.91 divided by 152.23 divided by 1000 minus 245.46 divided by 1000. So you can actually do this without doing this. Then I get the boiling point temperature was 331.54. So that will be my answer to this question.